In the middle of the 19th century, the height of a building was limited by a very human constraint, the strength of our legs. While we could technically build structures taller than 5 or 6 stories, few people were willing to climb any higher. In fact, the top floors of a building were often the least valuable, reserved for servants or low-rent tenants. This was the walk-up era, where the sky was a distant neighbor we could see but never quite reach comfortably. The bottleneck wasn't the masonry, it was the vertical commute. Mechanized lifts did exist at the time, but they were treacherous. They were primarily used in factories to move freight, powered by steam engines and suspended by simple hemp ropes. If a rope frayed or snapped, there was nothing to stop the platform from a catastrophic freefall. Because of this, no person in their right mind would step inside one. The elevator was a useful tool for cargo, but as a mode of human transportation, it was considered a death trap. To go higher, we needed a way to fail safely. The turning point came in 1854 at the New York World's Fair. An inventor named Elisha Otis stood on a platform high above a crowd and did something unthinkable. He ordered the suspension rope to be severed with an axe. The crowd gasped, expecting a disaster, but the platform barely moved. A heavy wagon spring had snapped open, jamming metal teeth into the guide rails and locking the platform in place. Otis looked down and calmly announced, "All safe, gentlemen." This simple safety brake transformed the elevator from a gamble into a utility. With the fear of falling managed, the next challenge was efficiency. An elevator car is heavy, often weighing several tons. If a motor had to lift that entire weight plus the passengers every time, it would consume an enormous amount of energy. The solution is the counterweight. On the opposite end of the steel cables, a stack of heavy weights balances the car. It's designed to weigh exactly as much as the empty car plus about 40% of its maximum capacity. This turns the motor's job from lifting weight to simply managing the difference in balance. In the early days, we used hydraulic pressure to move these boxes. Imagine a giant piston buried in the ground. Water or oil would be pumped into a cylinder, pushing the car up. This was incredibly smooth and powerful, but it had a literal physical limit. To push a car up 10 stories, you had to dig a hole 10 stories deep to house the piston. As buildings pushed toward 20 or 30 floors, the hydraulic method became impractical. We needed a system that didn't require digging to the center of the earth. The transition to electric traction motors changed everything. Instead of pushing from below, we began pulling from above. Steel cables are wrapped around a grooved wheel, called a sheave, which is turned by an electric motor. The friction, or traction, between the cables and the sheave is what moves the car. This allowed elevators to travel hundreds of feet without deep underground shafts. By the early 1900s, this technology allowed the birth of the iconic New York skyline, turning the top floors into the most expensive real estate in the world. As buildings got taller, the physics of the cables themselves became a problem. If you're in a building like the Burj Khalifa, the steel cables can weigh nearly 30 tons on their own. At a certain point, the cable becomes so heavy that it can no longer support its own weight, let alone the car. This is the steel cable ceiling. To go higher, engineers are now turning to carbon fiber. These ultra-rope systems are far lighter and stronger, potentially allowing for single elevator runs that reach over a kilometer into the sky. Engineering a fast elevator isn't just about the motor, it's about the air. In a modern skyscraper, cars travel at speeds up to 45 miles per hour. At these speeds, the air in the shaft becomes a wall of resistance. To solve this, high-speed elevators are often shaped like a capsule with aerodynamic cowlings on the top and bottom to slice through the air. Engineers also have to manage the air pressure inside the car to prevent the passengers' ears from popping painfully as they transition through hundreds of floors in seconds. The final frontier of the elevator isn't just vertical. It's horizontal. Traditional elevators are limited because only one car can fit in a single shaft at a time. If you want more capacity, you need more shafts, which eventually eat up all the floor space. New magnetic levitation systems, similar to bullet trains, are being developed. These multi-systems use magnets to move cars without cables. This allows multiple cars to loop through the same shaft and even move sideways, turning buildings into 3D transit networks where the elevator functions more like a subway. We often take the elevator for granted, seeing it as a mundane part of our daily lives. But without this impossible box, our cities would look entirely different. There would be no penthouses, no observation decks, and no urban density as we know it. The elevator didn't just solve a transportation problem. It changed the geometry of human civilization. By mastering the physics of the vertical, we didn't just build boxes, we built the modern world, one floor at a time.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.